So last times we have discussed the line configurations, the characteristics of different characteristics of link configurations. The three characteristics we have seen: topology, duplexity, and line discipline. And we have discussed in detail different line disciplines for point-to-point link, and particularly for we have given stress on multi-point link that is required for LAN or satellite communication systems. Local area network is most important, and in this context we have seen this for multi-point link. You can have pole and select line disciplines. Pole and select. Pole means the primary request data from a secondary, and select means primary has data to send. And also we have seen the different kinds of polling: roll call polling, half polling, etc. Roll call pollings, here the primary selectively polls the secondaries in a predetermined sequence, can be round robin fashions, right? And in case of half polling, that is used whenever there is a cluster of secondaries. I mean, primary and secondaries, their communication is possible through poll message. In that case, half polling, the central computer, the central primary, the polls transfer the polls message to the furthest secondary, right? And then secondary, it may add the data, or it may send the data, or it has nothing to send. So whatever the case, that information will be sent to the say nearest secondary. And if the secondary, nearest secondary also does the same things, if it has any message to be communicated, then that will be added to the tail of this the message, received message. So in this way, there will be relay type of message will be there, and the composite message will be related to the primary, and that is passed through the front end processor to disassemble the message, and if any data message, valid data message is there, then that will be sent to the primary for further processing. So these things you have seen it. So different kinds of pollings, etc. Timing diagram also most important. Now we'll see the application of these things in actual protocols. So so far we have discussed this. The sending signals in a transmission link, but for if you see the actual digital data communication systems, then many things are needed. Many things are needed, that will see it. Many things are needed to control and manage the exchange. Whenever there is a need of exchange of data for digital data communication systems, then many things are needed. Many more things are, whatever I have seen, many more things are needed to manage the exchange of data. In fact, now we'll focus on the sending data over a data communication link. So far we have considered the simple transmission link. Now we'll consider the data communication link. So to achieve this, achieve the necessary control, I mean, just now I mentioned many more things are needed to control and manage the exchange. So to achieve this type of control, and a particular layer of logic is required in the systems. In fact, if you see the data communication systems, there are protocol architectures are there. That can be 7-layer protocols, can be 5-layer protocols. Generally, it is 5-layer protocols. The practical case is 5-layer protocols. So the most bottom layer is the physical layers. I mean, that deals with the physical interfacing that we have seen. Last few classes we have discussed the physical interfacing, but that physical interfacing is not sufficient for the exchange of data between the two stations. So an extra layer is, an additional layer, a layer of logic. In fact, a layer of logic is added above the physical interfacing to achieve this the data exchange, to achieve the control of the data exchange, right? And whenever this protocol is used and layer, a particular layer, that almost a layer of logic is required to control the exchange of message, then whenever this protocol is used, that time the transmission medium between the two stations is referred to as the data link. That we call the data link. Transmission medium will be termed as data link. So we'll focus on these things, data link and data communication link, and we'll give emphasis on this, the layer of logic which is above the physical interfacing, which is needed for that exchange of data. And if you see these data communications objectives, if you see what are the objectives, if two stations are the transmitter, two stations, if you just consider two stations, they're exchanging data, primary, secondary, then you see what are the requirements, what requirements are there. Requirements are objectives. If you see requirements, these are most important requirements for exchange of data between the two stations. The number one is frame synchronizations. Frame synchronization. Frame synchronizations. Here actually we have seen it. It means beginning and end of each frame must be recognized. Beginning and end of now we'll see. We have seen the data are not transmitted simply bit by bit. It is generally it is in the form of frame. That frame contains the payload, control informations, and some flag, etc., etc. So frame synchronization is needed for exchange of data between two stations. Number two, it needs flow control. Flow control, that is the flow control. Why it is required? I mean, here the one station transmits, other station receives, but the sending station should not send the frames at a rate faster than the receiver can absorb. Right. If it exceeds, then one. If it does not, then overflow will be result. That will see it. So some sort of flow control must be there. Right. Number three, there must be error controls. Error control that we have seen also, bit errors may be introduced by the transmission mediums, and that must be corrected. That is the error controls. Number four, addressings. Addressing also required, particularly when you consider the multi-point links. Addressing required. I mean, say for LAN, if in case of LAN, two stations, if they want to exchange of data, then they must be identified. They must be specified which one is transmitting and which one is receiving. I mean, primary, secondary should be identified. So addressing required. So that is the another requirement. Number five, control and data. Control and data, they must be on the same link. They must use on same link. And if different paths are there, then there will be wastage of resources. So control separate communication path generally is not desirable for control informations apart from the data. And also the receiver, say data, one path must be equal. If you use another path for control information, that will be the wastage. I mean, that is not desirable. So same communication path should be used for control information as well as data, and the receiver must be able to distinguish the control informations from the data. That is the fifth requirement. And sixth is the link management. That is also required. Link management. link management, here some procedures for management. Some procedures are required, like for management, like initiation, maintenance, and terminations. So procedures are required for the management of these things, right? Initiation, maintenance, and terminations for our data exchange, right, between the two stations. So these are the requirements for exchange of data between two stations. So these are not satisfied. If you see, all these things are not not satisfied by the physical interfaces. So and a layer of logic is required above interface, above the physical layers to fulfill these requirements. In fact, data link protocols, data link control protocols, it can satisfy these requirements. And in fact, it is a complex affair that will see it. So, how, in what way this protocol can overcome all those things? In fact, there are two mechanisms are there, two techniques are there for data link control. Two techniques are there for data link control. One is flow control. Flow controls, and there is error controls. Different protocols are there that you'll see in details. Let us first discuss the flow controls. So, what is this flow control? What is this technique? In the flow control technique, you see here the so one is transmitting, one entity is transmitting, and other entity is receiving, and so one is transmitting entity, another is sending entity, a transmitting entity, another is receiving entity. So here in this technique, the transmitting entity will not provide the burden to the receiving entity. It will not overwhelm the receiving entity with data. When data is actually, when data are exchanged and it is received by the receiver, immediately receiver will not pass this data to the higher layer levels, higher layer of protocols. There are different, I told you, 5 or 7 layer protocols are there. So bottom layer is the physical layer, next is data link layer, next layer will be network layer, next we'll see it, all those things, network layer, next will be transport layer, next presentation layer, or maybe application layer, transport layer, next maybe application layer, or maybe in some cases it can be presentation layer, application layers. So there are different layers are there. Whenever the data is received by the receiving entity, it will not immediately pass the data to the higher layers. Whether it will do a certain amount of processing before passing the data to the higher level software or a higher level layer. So if this flow control technique is not there, then what will happen? The receiver buffer may fill up and overflow will result. Receiver buffer may fill up and overflow results. If this flow control is not there, right? So for these things, flow control technique is required. So basically, what is flow control? Flow control is some kind of it's a technique that through this technique, transmitting entity does not overwhelm the receiving entity with the data. Right. What are the actual protocols? The different protocols are there. One protocol is for flow control mechanisms. One mechanism is stop and wait flow control. Stop and wait flow controls. This is one mechanisms for flow controls, and it is the most simplest ones. In this case, you see here the source entity will transmit the frames, and the receiving entity or the destination entity will receive the frames. But you see, the further frame will be transmitted by the transmitting entity if it accepts, if it receives the acknowledgement from the receiving entity. That means as soon as the receiving entity receives the data, if it is ready to accept further frame or further data, further frames, frame of data, then it can send the acknowledgement. It will send the acknowledgement, right? Just saying that it has received the data and it is ready to receive the next frames. So acknowledgement will be sent if it is ready to receive the further frames. So you see, so then in what way it can control the flow control these flow control mechanisms? It can work on this work on this workflow like that. So you see, so the destination entity or receiving entity, actually it can stop the flow of data by not sending the acknowledgement. Right. So that is the mechanism of stop and wait flow controls. Right. Am I clear? So once again, the transmitting entity will transmit the frames, and the receiving entity or the destination entity will receive the frames, and further frame will be transmitted if the transmitting entity will get the acknowledgement from the receiving entity. So the further frames will not be transmitted if the destination entity does not send the acknowledgement. That means by withholding the acknowledgement, the flow of data can be stopped. So the destination entity can stop the flow of data by not sending the acknowledgement. But this works fine for large frames. This works for large frames. The stop and wait flow control works for large frame. But in practice, if you see, in some cases, the source does not send the data in a longer frames. Rather, it will send the data. It will break the data frames into smaller blocks, larger block into smaller block, and transmit the data in many such frames. Why it is why this smaller block is used? The reason for smaller block is reason for smaller block regions. If you see last, but it is stop and flow control. That means stop and flow controls. It will not. I mean, it is not sufficient. I mean, it is inadequate, as you can say. It is inadequate in case of smaller frames, but it works fine for larger frames. Now the question is why this longer data frames it is broken into a smaller data frames. That is because number one is this you see number one regions. Number one it is this the buffer size is generally it is small. Buffer size long frame is more buffer size is required. Large buffer size is required. That will be a costly phenomenon, right? So generally buffer size limited. That is one reasons. That's why the larger data frames is broken into smaller data frames. This is one reason. Another also most important is uh, if longer the transmissions, if I mean if the larger data frame is used, then more errors will be there. More errors will be there. For larger frame, the frame is large. For larger frames, you see, okay, more errors will be introduced. More errors more errors will be there. Longer transmission, obviously more errors will be there, and if it is required to retransmit, then it has to retransmit the entire frames. So in case of errors, retransmissions of the longer frame will be required. Retransmission of entire frame. A small error is here, but it has to retransmit the entire frames. Right. But for smaller frames, you see, errors will be detected quickly, and that times only a smaller amount of data will be required to retransmit. Right. So these two are the regions. Another region is this. You see, another region is if longer frame is used, then a station will occupy longer times for transmission of the particular for LAN. Say when shared medium is used, just like LAN, local area networkings, that times you see if a particular station occupies the longer period of times, longer period occupies the medium for an extended period, that is not desirable. That means other station will have to wait for the transmission of the frames, transmission data frames. So the thing is in shared mediums like LAN, it is generally desired not to allow one station to occupy the mediums for an extended period, right? Because that will cause the delay to the other stations. Try to understand these ones. So if longer frame is used, then there will be delay for the delay will be there for the other stations or other stations, right? So these are the three basic reasons why the larger frames are not used in data communications. So if you consider, if you use the stop and flow controls, so that is I mean this works fine if the frame is large, right? But the large frame generally not suitable for these cases, right? So in that case, more smaller frames are needed. So that's why stop and flow controls it's not adequate in case of and it doesn't work properly in case of the larger frames. So what we have seen it in stop and flow controls, you see it here, block diagram forms. Just I mentioned there can be physical layers. This is a physical layers. Next will be above this physical layer there will be data link layer. This is a physical layer, data link layer, and next above this there will be network layer. We'll see these things in network layer. Will get data. Here you see from network layer. So generally there will be application layer, say user data, user applications, and application layer. So user data will be passed to the presentation layer or session layer or transport layer. Next there will be the network layer. Next network layer it will go to the data link layer, right? So if you see the exchange data link layer, next it will be communicated to the other station through the physical layers, physical interfacing, physical layer through guided or unguided mediums. So you see it here. There can be network in betweens. In the other side, also same thing will be there. Physical interfacings will be there. Say that the frames are being transmitted. Frames. In the frames there can be data and some control function will be there. Here also there will be physical layers. Physical layer. Next there will be data link layer. Next will be network layer. So here the same way. First it will be received in the physical layer. Next it will go to the data link layer. Next it will go to the network layer. These things. Reverse process also will be there. The same things for full duplex operations or bidirectionals. The same thing will be. I mean here. Acknowledgement also will be there. Acknowledgement may be there in this way, like these things. So here also it will be like these things. So so in this case you see stop and flow controls. Sender sends one frames. Sender frames sends frames, right? Sender frames. Sender sends the frame and stops until it receives the acknowledgement from the receiver. Means then that means okay to go ahead. This type of instruction should be there. Unless it gets the information from the receiving entity, it will not transmit the further frames. Then sends when it gets the signal. I mean when it receives the acknowledgement, then it will send the next frames. So traffic can be there on the forwarding channels and the reverse channels at any times, because either data frames or acknowledgement frames will be there. So it needs some sort of half duplex link, right? Anyway, these things are there. Many more. These things will be more clearly understood if you see the timing charts. Timing charts. Before that, you see some parameters are to be defined. The bit length of the link. So you have considered the bit data length. So what is bit length? Bit length of link. Bit length of link. Yes. Anybody wants to say something? Anybody wants to say something? No. So bit length of a link, that is B, actually it is R into D by V. So R is the data rate, where R the data rate, and D the length of the link, length of the link, and V the velocity of propagations. Velocity of propagations, meter per second. Right. Data rate, length of the link. So bit length of the link B is this one. Bit length means it is the number of bits present on the link. That is the meaning of these things. Length of the link in bits. Right. That is the meaning of this, the bit length. When the length of the link is that, there will be two cases. You see, when the length of the link is greater than the frame length, or when the length of the link is less than the frame length. So consider the two cases, and you'll see it that when the length of the link is greater than the frame length, bit length is a bit length. If it is greater than the frame length, then inefficiency will be there. But never in both cases utilization efficiency will calculate it. It will not be 1. I mean, it is less than, always it is less than 1. I mean, always in both cases, whether link length is greater than or less than the frame length, here link always will be underutilized. We'll see. Let us see. It is what I have just mentioned. This comment, you can verify it. Say this is the first case when the link length is greater than the transmission times. That means it is A case 1 when A greater than 1. A is normalized value. What is this A? I am just telling you. A actually it is the propagation delay. It is a propagation delay. Right. And 1 is the transmission time. It is normalized. The transmission time it is normalized to 1. That is, this indicates the transmission times. So if you consider the two stations, transmitter and receiver, you see if you how many snapshots you get it. You see the case 1 when the link length or the propagation delay large means the link length is quite large compared to the frame length. You see it here. Try to understand this timing diagram. Already you have seen how to calculate. Now the you'll understand these ones. This is the transmitting entity. This is the receiving entity. Right. This case, this is the time t0 when starts transmission of the frame. So you see it here. The frames just started transmission. Right. The t0. Next, you see, next phase is T. Such cases, such 5 cases will be there. So let us draw the 5 cases. One more case will be there. These ones. So here in this case, T0, if it is 1, I mean T0 plus 1, the initial times. Next it is T0 plus 1. 1 just I mentioned, it is transmission times, right? Time for the station to transmit a frames. This is the time taken for the station to transmit a frame. So T0 plus 1 means it has completed its transmissions. So the frame has been completely transmitted. You see. So this is the frame. The frames completes the transmissions. Now it will propagate. It will go to the receiving stations. Right. So this is T0 plus 1. Now if it is, so when this frame will receive, when the first bit of this frame will reach to the receiving stations, you see TR. So it is, if A is the propagation times. So if it you see it, if it is so the time, the first bit of the frame will just reach the receiving stations at the time. This is T0 plus A. T0 plus A. But A is the propagation times. Now, this case, the frames will be completely received by received or completely absorbed by this A. That will be T0 plus A plus 1. Right. So that times it will be completely absorbed by this, completely absorbed by the receiving stations, and immediately it will send the acknowledgement. Right. It will send the acknowledgement, and at the times you see the acknowledgement, when the acknowledgement will be received here, the acknowledgement will be received when it is T0 plus A, twice A will be there, T0 plus twice A plus 1. So that is this ones. So this is the case when the link length is quite large, as compared to the transmission times of the frames. Right. There is another case is here, case 2, when the link length of the propagation delay is small compared to the transmission times. That time you see what happens. Two, 3, 4, and this is 5. So in this case, you see at T0, it is same as this. It starts transmitting TR, 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 TR. So you see so in this case A less than A, that means here at T0 it just starts transmission of the frames, right? At T0, similarly at T0 plus A, if you consider it is not T0 plus 1, it is T0 plus A, that times the first bit of these frames will reach to the front end of the frames, or first bit will reach to the you see still it will not complete the transmissions. Before the completion of the frames, the first bit will reach here. First bit will reach at A, that is T0 plus A in this case. And next it is this is when the it completes the transmissions, that will be T0 plus 1. Here you see it completes the transmissions. It completes the transmissions. So that is T0 plus 1. And you see when the full frame will be absorbed, that is T0 plus 1 plus A. That times the complete frame will be received or absorbed by the receiver, right? And immediately it change the acknowledgement. So when it is T0 plus twice A plus 1, that times you see the acknowledgement will be received here. Acknowledgement will be received by the transmitter ACK. So you see that is the case for A less than 1. So in this case, just I mentioned A1 is the transmission times, and it is normalized to 1, and that is A. A means it is propagation delay, that is actually B, that you have to find this bit length B divided by this L, right? The length of the frame in bits, the number of bits in the frames, these ones. Okay. So it is normalized, it's a normalized parameter. So when A less than 1, if you just compare these two cases, less than 1, that means the propagation times less than the transmission times, then frame is sufficiently long. That means what that means, sufficiently long, and the first bits of the frames will arrive at the destinations before this source will complete the transmission of frames, right? So that is the case of a less than 1, and in case of a greater than 1, it will complete the transmissions of the entire frames before the leading bits of the frames arrive at the receiver. You see it here. When the leading bits of the frame arrive at the receiver, that times it has completed. The sender completes the transmissions, right? So in this case, actually, there is a case for longer distance and higher data rates, right? So you see the first four snapshots. The first four snapshots, it is for the data. The frame contains the data, and next the last one shows the return of the acknowledgement. And if you see it, both cases a link is little bit in this case you can have efficient utilization. Link is efficient utilized, right? But still link is underutilized in both cases. And the most case, the worst case is this: when a greater than 1, that times link is always underutilized. But in this case, you see, in some cases link is fully utilized. Some of the cases link is fully utilized. So the two things are there. And in this context, you can calculate the what I am mentioning, these link utilizations. These utilizations you see can be calculated like these things. What are the utilizations for the two cases? Suppose the frames are being transmitted in this case F1, F1, F2, like these things, F3. The frames are transmitted like this in long message. A sequence of frames are these ones, right? In this way, frames are being transmitted, right? And so station, say one stations will transmit and other station will receive. It will send, say, F1, right, and then send to station, the station 1, then stations 2 will send the acknowledgement ACK, and when it is received the by station 1, then station 1 will send the frame 2, like these things, right? In this case, nth frame will be transmitted, right? So the total times to send the data, we can write it that T is the total times for transmitting all the frames, nth frames, total times, as before we have seen it, that is T, that is N into TF, right? TF is the time to send 1 frames and receive 1 acknowledgement, right? This is for 1 frames, right? And so it can be, we have seen it, how you can remember, last class we have seen it, that is TF for transmitting 1 frames, that is T propagation will be there, plus T frames, that is the frame transmission times, that will be plus some processing time will be required, T processings, plus another T propagation will be this propagation for frame propagations, another propagation will be for acknowledgement, and also there will be acknowledgement transmission times, ACK, plus there will be some processing times will be there for further these ones, right? So these things are there, we have seen it, and generally these processing times, these are very small, right? These processing times, this is very small, and also acknowledgement times also very small compared to the data frames, right? It's negligible, very small compared to the data frames. So we can write the total frames T, total frames T, in the modified form. You can write it N, total times, say these ones can be modified, it is T, it is N into 2 of T propagations. You see this one, these others are very small. This one you can neglect. This one's only 2 T propagations will be there, plus T frame will be there, T frame will be there, right? And if you just notice it, n into t frames, that is the time for transmitting the data for nth frames. Time for transmitting the rest will be the overhead. So the utilization efficiency or efficiency of the line, utilization efficiency or efficiency of the lines, efficiency of the line U. Just a minute. So U that is n into t frames divided by this n total times n into 2t propagations plus t frames. Right. So this will be like these things. T frames nn will cancel. T frame will be just divided by t frames, and if you set a actually this propagation delay, that is actually t propagations by t frames. That is the a. So if you consider this ones, then that will be 1 by 1 plus twice a. So that is the actually a is the propagation time by frame transmission times, right? So it is the maximum utilizations of the link, these ones. I mean, that means it is always less than 1, whether it is a greater than 1 or it is less than 1, and both cases a link will be underutilized. Maximum worst case will be there when a greater than 1. So these things are there. And the same things, this one can be understood if we just say a less than 1. Just you see it here. When a less than 1, you see less than 1, the link's bit length, that means bit length. I mean, the length of the link is less than the frame transmission. That times you see the station begins, the transmitting station, sending station transmits the frame at time t0, right? And at t0 plus a, you see t0 plus leading edge of the frames will just reach the r, right? And still at that time still t is transmitting the frames, leading bits reach here, but still it will not stop. It will still it will continue to transmit the frames, right? And when it t0 plus 1, that times it completes the transmission t0 plus 1, and when the frame will be completely absorbed by a, that is observed by this r, that is t0 plus 1 plus a. So r will receive this. When r will receive the complete frames, then immediately it will send the acknowledgement, and at t0 plus twice a plus 1, that times it will be acknowledgement will arrive at station t. So the total times, if you just see total time elapsed, it is 1 t0 plus twice a plus initial time t0. The time elapsed, it is twice a plus 1, isn't it? So and total transmission time is 1, hence the utilization will be same as is 1 by 1 plus twice a. So from this logic also, it is this utilization efficiency, it is less than 1, right? Just this I'm showing for a less than 1. Same thing will happen for also a greater than 1. But anyway, you see it here, link is underutilized. In this case, link is certainly utilized, but still it is some of the cases it is underutilized. So stop and flow controls drawbacks are there, but serious drawback will be there when the bit length it is greater than the transmission time of the frames. Anyway, so today this much. Next time also, the advantage is it is a faithful process, means each frame is acknowledged, next frame will be transmitted. So it's a faithful, each frame is checked and acknowledged, next frame is sent. But it's a very slow process. So if you do these, follow these protocols, the internet, nobody will access the internet. For downloading one, say, movie, it may take several hours, right? So to avoid this one, we will see some advanced the protocol, that is sliding window flow control. Here, several friends can be transmitted simultaneously. But next time we'll see it. Anyway, if you have any questions regarding this diagram, you can ask. This is most important. For concept, most anything. If anybody, if you have any questions, you can ask. Anybody, any questions, you can ask. Your quiz will be tomorrow at 6:30. Mr. Vardhan, already I told you, those who are listening must note it. Your quiz will be tomorrow at 6:30 p.m. Please respond.
Yes, sir. Yes, sir.
Okay. If you have any questions regarding these things, you can ask. One or two questions, sir. Welcome. If you have any questions regarding this stop and wait flow control, कोई किसी के क्वेश्चन है तो पूछो. किसी का कोई क्वेश्चन है तो पूछो. नहीं है क्वेश्चन? है कि नहीं है बता दो. हम स्टॉप कर देंगे. कोई किसी का क्वेश्चन है?
No, sir.
No, sir. Okay.
No, sir.
Okay. Just wait. Okay then.